in the talk by who gave the talk yesterday? You yesterday about the characterization of orderability in terms of cones, positive and negative cones. So the characterization is the following: G is left orderable if and only if there exists a decomposition of G that I will write in this way. So G is the disjoint union. This is for disjoint union of P and P inverse and the identity, and this is a semigroup. Okay, and P inverse is the semigroup made by the inverses of elements that are here. Okay, and well, the fact that semigroup just means that if G is in P and H is in P, then the product of G and H also is in P. Okay, and well, this is an exercise. This is a real exercise, but I will give the proof because it's really important in order to put the hands on some orders, on some specific groups. So assume that G is left orderable. So you have a left order on G, and then there is a natural semigroup P. So P is called the well, here is totally general, but if you want to produce, starting from this decomposition, a left order, if you start with a left order and you produce the semigroup P, this is the set of elements which are larger than the identity, and this is called the positive cone. Of the order. So this gives you the positive direction in the group. Okay? And this is a semigroup because if G is in P and H is in P, well, if H is in P, this means that H is larger than the identity. Yes? And then you can multiply always on the left by G. Then you have GH is larger than G. Okay? But G is in P, so G is also larger than the identity. Okay? So GH is larger than the identity. This means that GH is in P. Okay? So the positive cone of a left order is a semigroup. And the converse, well, if you have the decomposition of G this way, then you can define an order on G by letting, say, G is larger than H if and only if H inverse J is in P. H inverse is in P. Okay. Okay, this is the natural definition because if you have this inequality, this means that H inverse G is larger than the identity. So this is the element you should include in P. Okay? And well, this is a total order because if you have two different elements, then one is larger than the other one. So say G is larger than H, and then this element is sorry. I will give you. So this is a total order because if G is different from H, then either G is larger than the H, sorry, either H inverse G is in P, or the inverse of this, G inverse H is in P. Or if you wish, H inverse G is in P minus 1. Okay? Because this element is different from the identity. In this case, well, the definition says that G is larger than H. And in this case, the definition says that H is larger than G. So you can compare any two different elements. Okay? And the other condition is the transitivity. Of the order that you produce this way. So if you have G, say F larger than G, and G larger than H, well, this means that G inverse F is in P. Okay? And this means that H inverse G is in P. Okay? And then P is a semigroup. So you can multiply these two elements. So H inverse G times G inverse F is also in P. Okay? And well, this G disappears. So H inverse F is in P. And this by definition means that F is larger than H. Is it okay? Okay, so this is a translation of the notion of left orderability to the context of positive cones. And in some cases, it is easier to give the cones order rather than the definition of the order itself. So let me give an example. So remember, I think nobody sees it. Is it okay here? Okay, so remember yesterday we have c to the square. Okay? Yeah, I think. Okay, now it's okay. Okay, so you take c to the square, and we gave an order which was a lexicographic order. So you compare the first coordinate. If they are equal, then you pass to the second order, to the second coordinate. So one way to say this is just by giving the positive cone of the order. So the positive cone of one of these orders, because there are many lexicographic orders, is the following. So you take A and B, the pairs of numbers A and B, integers numbers. So either the A is positive or A is equal to 0 and B is positive. Okay? This is the positive cone of an order on c to the square. Okay? So if you go to the Cayley graph, so here is the identity, and this is the A direction, and this is the B direction. Okay. So what are the elements which are positive? So the positive elements are those for which A is larger than 0. So all these elements here are positive. Okay, to the right of this axis. And the elements for which A is equal to 0, but B is positive. So this point here is also positive, this point is also positive, and so on. Okay? This is P. And P inverse is, well, these points here. Okay, this is the semigroup P inverse. It's okay? And there is the identity, which is neither positive nor negative. But actually, well, there will be a talk about orders on abelian groups. There are many ways to order the abelian groups. So yesterday we realized C to the square as a group of translations. So this produces many orders by pulling back the order on the real line. But this way you can also see that. So for instance, you can consider the following thing. So I will consider again the Cayley graph of C to the square. And I will draw a line passing through the origin, and I will consider a line which is which has irrational slope. Okay? So no point of integer coordinates is in this line. Okay? Okay? When I have such a line, I get an order on C to the square, because I can decide that, well, this set of points, those that are above the line, is the positive cone, and this is a semigroup, okay? Because this is a set of points, if you wish. The half plane is a semigroup because this is the set of points that are positive for a certain linear functional, which is just taking the inner product with respect to this direction, okay? And this is the set of negative elements, okay? And this is an order, and this way you produce irrational orders on C to the square, okay? Which was essentially equivalent to that. Yesterday we took a realization of C to the square as the group generated by one and some irrational number, okay, inside R. This is essentially equivalent, okay? And you may ask, what happens if instead of taking a line with irrational slope, I take a line with rational slope, okay? For instance, this is what happens there, except for that the slope there is infinite, okay? But this is infinite is rational, okay? in this, well, infinite is, well, okay, this is projective way of thinking. Okay, so when you have a rational slope, you will have some points in the line, and the only thing that you have to do is to decide which part of the line will be positive and which part will be negative. Okay. For instance, in the lexicographic order, I took. So this is the line. Okay, this is the critical line in this case. Okay, and I took this part of the line as being the positive one, but I could make the other way. So I could consider this also as an order, and this is just by declaring that the second condition is changed into A equal to 0 and B negative. Okay, and this is the new order. Okay. Okay, so there will be a talk on this, because if you go from C to the square to C3 and C4, this becomes harder. But essentially, there is a description of all F orders, all orders on torsion-free abelian groups. Okay. Now I want to give an example of a group that I like very much, and this is somehow my favorite example, because it gives you examples of many things, many strange elements in the groups and so on. So, and it's related to a question of Pierre yesterday. So I will take G. This is the pi 1 of the Klein bottle. So this is a non-orientable surface, okay? But the pi 1, this group is still left orderable. And this is really very, very nice. So let me remind one of the presentation of this. So this is the group generated by A and B. And one way to write this is, I prefer this way, BAB equals to A. Okay? This is essentially, so you take the square and you consider this as the A direction, and this is B, and okay. So BAB equals to A. Okay? BAB equals to A. Okay? If you do the identification, then what you get is the claim. Is it okay? Well, this is a left orderable group. Okay? And I will give you the description of this. So the first thing is that there is a remark. And the remark is the following. So G, this group G, the pi 1 of the claim bottle, may be written as the disjoint union of the semigroup generated by A and B and the semigroup of the inverses. So this is the semigroup generated by A and B. So this is the set of elements that may be written as combination of A and B with positive powers. Okay? And G is also the disjoint union of the semigroup generated by A and B inverse, the inverses of this semigroup and the identity. Okay? This is just a picture. I will draw the picture. So forgot something. Okay, I forgot something. Okay, I will draw this and I will come back to some remark. I forgot to say something. So what is the, I will draw the Cayley graph of this group. So this is very close to the Cayley graph of C to the square, but I will draw the oriented Cayley graph. Okay, so here is the identity, and this is the A direction, and this is the B direction. Okay? So what I'm saying here, so I will consider the semigroup generated by A and B. So I have the right to go from, so this is A. But remember that the relation is that B goes this way here, A goes this way, but B goes this way here. Okay? A goes to the right always, but then B goes this way. Okay? Then A goes to the right, and B goes down. Okay? So if you start with the identity and this is B to the square, this is A, this is A, B, this is A, B to the square, and so on. So all the points in red here belong to the semigroup generated by A and B. Okay? It's okay? And if I consider the semigroup of the inverses, which means the semigroup generated by A inverse and B inverse, then the points that appear are those that in the other that are in the other half of the group. So here. So this is the semigroup A B inverse. So the semigroup of the inverses of the other one. Okay? So this is this picture corresponds to this the composition. Okay? And if you see, this is very close to this, the composition, except for one thing. So here the semigroup is generated by only 2 elements. Okay? And I leave you as an exercise to show that P is not finitely generated in this case. This is a crucial difference. In the case of the abelian group, the semigroup is not finitely generated, but in this case, we have the same picture, except for the orientations. In that case, the semigroup is finitely generated. Actually, it is generated by 2 elements. Okay? Well, the picture for this decomposition is almost the same. So in that case, I think that these elements turn to be green and these elements turn to be dry. Okay? Well, I have one claim, one consequence of this decomposition. So in particular, it is hard to imagine such a decomposition for a line with irrational slope in the case of the Klein bottle group. It's different. Okay. So corollary of this is that the pine one of the Klein bottle has exactly 4 left orders. Okay? Okay. So what is an example of a group that has 2 left orders? Well, is the group of the integers. Okay, the group of the integers you can order in the canonical way or in the reverse way. So this is actually, and this is important. This is a remark that I forgot to mention at the very beginning. Is that, well, when I have my decomposition G equals to P union P inverse union the identity, you can choose P as being the set of positive elements for an order, but you can also choose P minus 1 as being the set of positive elements for an order. This is like reversing the natural order, if you wish. This is what happens in the integers. This is totally general. Okay? So what these decompositions give immediately are 4 left orders on the Klein bottle group. There is 1 left order for which this is the positive cone. This is another for which this is the positive cone. There is another one for this is positive cone, and finally you can take this as the positive cone. Okay? The point is that there are no more orders than this. Okay? You cannot order the pi 1 of the Klein bottle in a different way. Okay? And the proof is quite easy. So you take A and B. Okay? There are 4 possibilities, of course. You may have A positive and B positive. You may have A negative and B negative. A positive and B negative, A negative and B positive. Okay? So let's take one of these possibilities, any one. For instance, this one at random. Okay? If A is positive and B is negative, this implies that A is positive and B inverse is positive. Okay? And then when you have positive elements, you may multiply them and you will always get positive elements. So the whole semigroup generated by A and B inverse is contained in the positive cone of the order. if you have an order on so we start with an order on the pi 1 of the claim bottle. Okay? So in this case, this semigroup is contained in P. It's okay? And of course, the semigroup of the inverses will be contained in P inverse. Okay? It's okay? So we knew that the pi 1 had this decomposition. P equal, the pi 1 is equal to P union the pi inverse union the identity. Okay? But P, in this case, contains this. And, well, if P contains this, then P inverse contains this. Okay? And there is no more room to move things. So we have completely determined the signs of every element in the group. Okay? So the order is the order for which this is the positive cone. There is no other possibility. And of course, in any case here, you can match the corresponding case to one of the semigroups there. Yeah.
Is it possible to make this group a little bit more abstract and for something like if I have a group with an order with a cone finitely generated plus a few conditions and it has only finitely in an order? Does it apply to slightly more general groups?
Okay. No. I want to give. So there are two ways where you want to go. So one thing is trying to determine groups with finitely many orders, because here there is more than a finitely generated positive cone. There is two different decompositions that give you all the orders. Okay? So this is okay. Let me give an example to explain this. So you take the bounds accelerator group 1 minus 2. Okay? So this is the group generated by A and B. And I will change the presentation here to explain this. Okay, so I have the identity here. So this is the A, B, A inverse equal B inverse. Okay? So A conjugate B into its inverse. Okay, so here A conjugates B into the square of its inverse. Okay? Exercise has only 4 orders, like in this case, but the positive cones are not finitely generated. So the properties of having finitely many orders are not equivalent to that. Is not equivalent to that. The positive cones are finitely generated.
I didn't change that.
No, because it wasn't a question. I mean, you can ask many natural things. So I will give another kind of remark on this. Yeah.
So as a follow-up, what if your presentation has, you have a finite presentation with only positive powers appearing?
Yeah. Okay. I will try to. I will give 2 more results in this direction that somehow explain what's happening. Okay. The second thing is that there is a theorem by Tararin, okay, from Russia in the 80s, that completely classifies groups with finitely many left orders. Okay, this is a complete classification of groups with finitely many left orders. I will not state the theorem because it's a little bit technical. All these groups are solvable, but what's happening is that somehow at each step, what you add is an element that reverses the orientation of the previous elements. Okay, so for instance, take the group generated by A, B, and C. So A conjugate B into its inverse, C conjugate B into its, no, B conjugate C into its inverse, and I think you can put here A and C commute. Okay? And you can check that this group has 8 left orders. So you have all the decomposition, A, B, C, A, B inverse, C inverse, whatever you like. Okay? And here is the point, is that A is reversing the orientation of B, and B is reversing the orientation of C. Okay? If you preserve orientation, then you have something like an abelian group, and in that case, you can do this trick of taking lines of irrational slope and produce many left orders. Okay? This is somehow what happens. But this is a very nice theorem. Okay? And this is not really hard to prove. I mean, this is completely elementary to give the classification of all groups with finitely many left orders. Okay, and the last point that I think this is a better answer for the question of Pierre is that this is a remark by Peter Linnell. Okay, which says the following. So forget about the possibility of determining all left order on the group, and that all left order are finitely generated as, and so on. So let us assume that we have a left order on a group such that the positive cone of the left order, I will denote this way. So this is the positive cone associated to these left orders, is finitely generated. Finitely generated as a semigroup. So there are finitely many positive elements such that every element writes, every positive element for the order writes as a product of these elements with positive powers. And then the conclusion is that this is an isolated point of the space of left orders. So remember, we had the space of left orders, which is something which is totally disconnected. One would like to think that this is like a Cantor set, but this is not true because in that case it was just made by 4 points. But somehow in most of the cases it's like a Cantor set. But if you detect a positive cone which is finitely generated, you get a point which is isolated. Okay? And the reason, this is really a remark, okay? But this is a very important remark, actually. The reason is that if you have G, which is decomposed, say, A1 up to AK, are the generators of the positive cone. And, well, the inverses are the generators of the positive cone, of the negative cone, and so on. I can give you a neighborhood of this of the order, which is made only by this order. And what is the neighbor? So what is a neighbor of an order? Is the set of orders for which finitely many inequalities are prescribed. What are the finitely many inequalities that I will prescribe? Well, the fact that A1, A2, and so on are positive. If I do have another order for which these are positive, then this semi-group is contained in the positive cone, this semi-group is contained in the negative cone, there is no room to move anything, so the order is this order. Okay, so this is an isolated point. And what is important is that it is this way that many isolated points in the spaces of left orders were discovered. Okay, so at the very beginning, people thought that if it was infinite, actually it was a Cantor set. Okay, but actually this is not true. And the first example, I will come back to this. Maybe on Thursday, not tomorrow, this is for sure. But this is not an exercise, this is an example. But this was the first example of a group having infinitely many left orders, but having isolated points in the space of left orders. And this is the Bray group. Okay, I can give you a very quick presentation of the Bray group that I like very much. So the canonical presentation is you take sigma 1 and sigma 2. These are the hat twists, and you have the relation sigma 1, sigma 2, sigma 1 equals sigma 1. Okay? But I will just need the presentation of the group, so don't worry. Okay? So the presentation that I will take is another one. I will take the Bray group generated by A and B a to the square B equals to A. And I like very much this presentation. Okay? Here, A equals sigma 1, sigma 2 for the canonical generators, and B equals sigma 2 to the inverse. Okay? You can check that this presentation is equivalent to this one. Okay? And if you look, this presentation is very close to that of the Klein-Botto group. Okay? And one has this decomposition. Okay, for the Bray group, this is true, and this is still elementary. There is an statement for general Bray group, but if you pass from B3 to B4, nobody knows an elementary proof of that. So there are 3 generators in that case, but nobody knows how to prove it without using very sophisticated methods. But you have this decomposition. You have this one to prove it directly. So if you go from B3 to B4, then you have to pass through the Hornois theory to get the positive cone, which is finitely generated. Okay, it's really very hard. Okay, many people try to do that by elementary means, but it doesn't work. But you have only this decomposition. You don't have this decomposition. Okay? So this decomposition gives you an isolated order, an isolated point in the space of left orders. But actually, there are many orders in this group. Okay? There are many. There are uncountably many left orders in this group. Okay? Yes?
Have people studied groups of symmetries of the orders of homomorphisms of LOG?
You mean there is the action of G in LOG?
Yeah, but there may be more, right?
There may be more.
For example, if G is abelian, the action is trivial.
Yeah. You can act the group of automorphism of G in the space of left orders of G. Okay? In general, looking at the symmetries, so in general, the space of left orders is a Cantor set. For instance, if you take the free group, well, we know that the free group is left orderable. We don't have any explicit order, but we know it is left orderable. the space of left orders of the free group is a Cantor set. Okay. Now, if you look at symmetry of the Cantor set, is everything. I mean, okay. Okay. But
Because the minimum remark implies that if you have a group, if you happen to know that all for every vertical right order the positive cone is finitely generated, then they must be finite in any order. That's why it's compatible.
yes. 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 Yeah. But okay. So I will come back to that tomorrow because I will give some hints about the topology of the space of left orders and how to construct things and what's really happening there. Okay, and I will give the proof of the fact that the space of left orders of the free group is a Cantor set, without giving any explicit left orders on the free group. Okay. Okay, but I want to keep this example because I really like very much. So I will just pi1 of k, the Klein bottle, is the group generated by A and B. B A B equals to A, because it has many examples of things that I like very much. Okay, for instance, you have B A B equals to A, and you have if you multiply this by A, this is BA equals to A to the square. Okay, so this is BA to the square. Okay, so you have two different elements such that the squares are the same. Okay, and there is an order, but this is just a left order, so there is no contradiction here. This is impossible if the order is bi-invariant, but the order cannot be bi-invariant here. Okay, so my question is, which element is larger, BA or AB or A? So, sorry, I will consider this the composition. I didn't give the order, so this is a, and I will consider the order for which this is the positive cone. And the question is whether BA is larger than A or BA is smaller than A. Okay, well, you have to do some computations to check that. Be careful. The right one? This one? Yeah, this one. This one. Look. I can only multiply on the left. Yes? This is the point. So this is equivalent to A inverse B A is smaller than the identity. Okay? But what is A inverse BA? If you go here, A inverse BA equals to B inverse. Okay? And B inverse is in the negative corner of the order that I am. Okay? So A is larger than BA, but the square of A is equal to the square of BA. Okay? Okay, now this is a real exercise. I will put here for real exercise. Find in this group x and y, which are different, such that so x larger than y and x to the square is smaller than y to the square. Okay? Because here we only had two elements which were different, for which the square were equal. But I want the reverse inequality. Okay, another example in this group. Take x equal to A and y equals to A V inverse. So check that x is larger than y for the order for which this is a positive cone. Okay? And x inverse is larger than y inverse. It's just checking. Okay. Good. Okay. So okay. So now I will come back to free groups. Okay, and I will switch a little bit so that maybe you know, most of you know this stuff, but I will give a proof, a very short proof of the so-called ping-pong lemma by Klein, and I will show you how this lemma allows to produce free groups of homeomorphism of the real line, which means that the free group is left orderable. Okay, this is a proof. Again, the proof is not completely explicit. So you can manage to produce the free groups, but then to put the hands on the left orders is somehow difficult. But anyway, this allows to convince you that these kind of things exist. So the ping-pong lemma is a very general statement that says the following. So if you have a group, if you have two elements, two bijections, say F and G, there is no hypothesis on the space X, so there is no continuity, nothing here. Just F and G are bijections of some set X, and you suppose that A and B are subset of X, which are disjoint. Non-empty. Okay? And you assume that the following happens. So suppose that f to the power n of A is including B for every n different from 0, and f and g to the power of n of B is included in A for every n different from 0. Okay? Then the conclusion is that the group generated by F and G is a free group. Yes. And this is the canonical way to produce free groups, or to prove that some group is actually free, is to build some action on some space. No hypothesis on the action, so just an action by bijections and detecting two sets A and B, such that, so you have the space X here, you have A, B, and F always move A into B, and B moves B into A. And this is the ping-pong game. Okay. Start playing, and so on. Okay, and okay, very quickly, I will give the proof of this lemma. So this lemma is stated in many different ways in the literature, but I think this is the best way to state it. And the proof is very simple. So you take a word.
Actually, maybe you can say that because in practice, you don't even need to know that G, maybe action of G, but at the beginning you don't know that the map from G to the direction of X is injective, but at the end you will know it by the limit.
You say this? No?
I'm saying you have a map from the left to the right.
So F is a,
What I'm saying is that the proof will tell you that if you have a group which, I mean, in practice you have a group and you will define an action, and what the proof tells you is that the action is spaceful, and that the group is free, but you don't even have to check at the beginning
that you had an action.
not that the action is spaceful. If you wrote G, it's a detail.
This? No?
Okay.
No? No, it's the same.
No, imagine you have an abstract group generated by two, well, okay, no, forget.
Okay, forget. Okay, very quickly the proof. So you take a word. In F and G. So I will give the proof for an explicit example because writing all the statements is very. So I assume that omega is equal to Fg f to the minus 1 g to the square. Okay? And I want a word which is reduced, where there is no pairing of g and g inverse and so on. Okay? And what I have to prove is that this word is not the identity. So, okay. So what I will prove is that this element acts in a non-trivial way in the space X. Okay. Okay. I need a trick because there is something which is bad for this word, is that it starts with a letter which is different from the last one. Okay. So I will conjugate this word. So if you think a little bit, this can always be made. I will conjugate by f, and then I will get this word. Of course, proving that this word is non-trivial is the same as proving that this word is non-trivial. Okay? But I will keep this word because the first letter and the last letter are the same. And now I will look for the action of this word. So I will start with the set A. So I start with A. And here I have B. And I have F minus 1. F minus 1 moves A into B. Yes? And then G to the square moves B into A. And then F minus 1 again moves A into B. G moves. This was the starting point. Okay? And finally, F to the square moves A into B. So the conclusion is that F omega F inverse of A is contained in B. Is it okay? In particular, this cannot be the identity. Okay? That's a proof, essentially. Okay, so these kind of pictures appear naturally in this context because suppose that you have two elements, two Möbius transformations that are hyperbolic on the circle. So this is the classical picture of this stuff. So you have F and G. And I will suppose that they are very hyperbolic in the sense that I will draw the picture. So this picture means that the complement of this interval is mapped into this interval. Okay? So I have here F has a repelling fixed point, here it has a contracting fixed point, and there is some contraction towards this point. And I will suppose that this red, actually these are Euclidean circles. This circle is mapped into this one, which means that the complement of this, so the whole interval here, is mapped into this one. So I am contracting towards this direction. And G, well, for G the same. So there is some circle here, which is mapped here, so that the complement of this interval, namely this interval, is mapped into this one. Here there is an attracting fixed point for G. Okay? In that case, well, this is, I will denote this by A1, this part of the circle. This is A2. Okay? So I will only keep the unit circle part of the circle. And this is B1, and this is B2. And of course, A will be the union of A1 and A2, and B the union of B1 and B2. These two sets are disjoint. And we have that property. Because if you look at for positive iterates of f, well, it maps the whole interval here into here. So it maps B1 and B2 into A2. And the inverse maps B1 and B2 into A1, because it contracts in the other direction. And the same for G. It maps A1 and A2 into B2, and G inverse maps A1 and A2 into B1. Okay? Well, the conclusion is that the group generated by F and G is the free group intergenerators. Okay? There is no relation between F and G. And you can look why there is no relation because of that argument. So you can follow the action of F and G on this interval. So for instance, the action of G moves this interval into intervals here, and this interval is mapped into some interval here. F inverse maps these two intervals into intervals here, and this one into this one, and so on. So there is a Cantor-like dynamics that appears in this picture. Okay? Good. Well, this is a group of homeomorphisms of the circle, and what we want for the orderability issue is a group of homeomorphisms of the real line. But what you can do is to take lifts of these maps to the real line. So I will take some, we denote hat F and hat G will be homeomorphism of the real line that preserve the orientation and commute with the translation by 1. Any lift will work, and well, and you will take lifts of the sets A and B. Okay? To the real line. And you have the same picture, except for that the set A appears in the real line as a set, as a union, as an infinite union of intervals. So this is A, something like this. Okay? There are lifts of A1 and lift of A2, like this. A1 lift, A2, A1, A2, and so on. This part corresponds to A1 and A2, and so on. And for B, there are some other intervals which are disjoint. So these are the B intervals here. Okay? And, sorry, I should use this for A. And the new set A, the A hat will be the union of all these red intervals, and B hat will be the union of all these green intervals. These are disjoint, and you still have the properties that F hat to the power n of A hat is included in B hat, and G to the power n of B hat is included in A hat for every n which is different from 0. Okay? So you have this ping-pong dynamics, except for that these sets are infinite, but it doesn't matter. So the group generated by F and G, the conclusion is that the group generated by F and G is a free group. Okay? So what you get is a free group of homeomorphisms of the real line using this ping-pong procedure. Okay. Okay. Now to conclude, I would like to come back to this stuff. So we know that the free group is included in homeo of the real line, homeo plus of the real line, the orientation preserving homeomorphisms. And for us, this was very important because we know that all left orderable groups are here. At least all countable left orderable groups are here. Okay? Okay? So that this is a good space to look at, and moreover, in this identification, what we did was it was twofold, because starting from a left order on G, we produced an action on the real line. I will recall the action because it is important to keep in mind what we are doing. It's something somehow tautological. Is that we map the group into the real line in an ordered way. Okay? So the map I denote yesterday by P. To each point, to each element in the group, just associate a point. So this is from G into R, which is order, and some other properties in order to ensure continuity at the end. There was this issue here of taking the middle point whenever you had some intermediate elements and so on. But here you have some element P, say P of H, and well, this map is not surjective. You just have if you have a countable group, you just have a countable number of points in the real line. But there is a natural action, which is the tautological action. So G will map P of H into P of GH. Okay? And then this is an action which is partially defined, and there is a way to extend it continuously to the real line. Okay? This is really something tautological, but it is nice to look at this action and to trying to understand what's happening. For instance, let us consider this action, and let us suppose that the order is bi-invariant. Okay? Okay. So bi-invariance should somehow should appear in this dynamical realization in a certain way. Okay? One should be able to recognize that the order from which this action was constructed was actually bi-invariant. And there is a nice ways to to produce this, to recognize the biinvariance property. And the point is the following. So let me come back to this. And here, look, I suppose that G, so G is moving pH into P of G of H, and I suppose that this movement was to the right. Okay? This means that GH is larger than H. Okay? So in this picture, GH is larger than H. Okay? But one would like to say that this is equivalent to G being positive, but this is not true, because for that you will need to multiply by H on the right. Okay? But you are allowed to do that if the order is biinvariant. Okay? So this is equivalent if the order is biinvariant to that G is larger than the identity. Okay? This is equivalent. Okay? And this is independent of H. Okay? So this means that when you have a biinvariant order and you take any H, an element which is positive will move this H to the right. Any point of this kind will be moved to the right by a positive element. And similarly, if you have a negative element, every point of this kind will be moved to the left. Okay? So I will write that. I will write it here. Okay? And every negative element moves everything to the left. But of course, this is just at the level of the points of the form P of H. And the action by homeomorphism of the real line is obtained by taking by passing to the limit. So you will not have this strict inequality here for all points, but you will have at least some weak inequality. So in the dynamical realization, which means that the action that produces, starting with the order, you will have G of x larger or equal than x for every x now in R. If G is positive, and G of x is smaller or equal than x for every x in R if G is negative. Okay? Which means the following. So now I can draw graphs, because these are homeomorphisms of the real line, and this is the diagonal, and the graph of a positive element is something that which is always above the diagonal. It can touch the diagonal, but it cannot cross the diagonal. Okay, something like this. Maybe it's here, maybe here. Maybe there are infinitely many points which are fixed by the element, but it never goes to the other side of the diagonal. This is a positive element. Okay. And a negative element is an element whose graph is always below the diagonal. And I like this remark because, well, this is something that I didn't prove, but for instance, F2 is biorderable. I will at least sketch the proof of this. Okay, this is a classical set. In particular, there is an action of F2 like this. And this is very hard to imagine. Okay? It's an action of the free group such that if you take an element, either it's above the diagonal or below the diagonal. You cannot cross the diagonal. Okay? Okay? And there is another family of groups which are biorderable. Is the in general the group of piecewise linear homeomorphism of the interval. This group is biorderable. Okay? Okay, I will draw a picture to explain what is the order. Okay? So if you take two elements here, well, they are piecewise linear. So at the very beginning, they are linear. Maybe one is above the graph of one is above the other. Maybe they are equal. But even if they are equal, at some moment they become different. Okay, so suppose that this is the graph of f, and this is the graph of g. Maybe this crosses the diagonal and so on. Okay? Okay, maybe they are equal at the very beginning, but at some moment they become different. Whenever they become different, well, you say that f is larger than g because the graph of f at this point goes above the graph of g. Okay? And this is an order, and this is bi-invariant. Okay? Just check this. This is a bi-invariant order in the group of piecewise linear homeomorphism of the interval. In particular, if you have a finitely generated group here or a countable subgroup here, using this bi-order, which is very strange, you can produce another action on the real line using this stuff. A dynamical realization which is very strange. For instance, there is a famous group, which is Thomson's group, which is a group of piecewise linear homeomorphisms of the interval that has many other actions on the real line and has these kind of actions which are very special. Yes?
So you're saying f greater than g, you're defining by the first place f and g differ, you take whichever's above the other one?
Yes, yes, yes.
So with that statement that f is biorderable, are you saying that that is implied by the fact that you have an action like this on the real line, or are you talking about the reverse?
Okay. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. So I have to finish. So exercise, and this is a real exercise. The converse is true. Okay. The converse is true. Okay. Thank you. So we have this. So if G is biorderable, there is an action like this with this property of graphs that do not cross the diagonal, and conversely, assume that you have a subgroup G of the group of homeomorphisms of the real line, orientation preserving, such that this property holds. So for every G different from the identity, either G of x is always larger or equal than x, or G of x is smaller or equal than x for every x. Okay? For every x simultaneously. Then the group is biorderable. Okay? This is a real exercise. You just look at what we did yesterday. So starting with an action, we build an order. And you look what happens with that order, given that the action has this property. Okay? And you will check this is a bi-order. Okay? And tomorrow what I will do, I will start by looking at for instance, at the Archimedean property. What is the Archimedean property in terms of the action on the real line? Okay, I will transform this property, which is algebraic, into a property on the dynamics of the action on the real line. And what is the Conrad property? Okay, what is the dynamical content of the Conrad property for the action on the real line? And we will discover something which is very natural and related to some stuff that was widely known in the language of codimension 1 foliations. And then I will give a different approach to the Conrad theory using this dynamical approach. Okay, so thank you.